Right. See, everybody. Last class we learned about galvanic cell. I'll just give you a quick briefing and then we can start learning the uh, application. See, first session, what we learned is that terms like galvanic cell, wherein a chemical reaction is converted into electrical energy. Okay, this is a spontaneous reaction. For galvanic cells, we typically require two half cells connected by something called salt bridge. There will be two electrodes, and these two electrodes, we assign the left part of the electrode as anodic cell, right part as the cathodic cell. A voltmeter is connected to read how much voltage it is built up. The amount of voltage that you will get is measured as E cell, and that will be E of oxidation plus E of reduction. We learned that E cell can also be represented as E naught of reduction happening at cathode minus E naught of reduction value of anode. Then we learned that there is electrolytic cell where an electrical energy is being supplied to carry out certain chemical reactions, and this is a non-spontaneous change. We are trying to make a non-spontaneous change into spontaneous form or a possible chemical reaction by using electrical energy. In this case, you will have only one cell. Within the same cell, we have cathode and anode. These are connected by external electrical wires with some voltage on it. And irrespective of whether it is an galvanic cell or electrolytic cell, reduction always happens at cathode, oxidation happens at anode. In galvanic cell, electrons are accumulated on cathode and positive charge is accumulated at anode, at cathode. In electrolytic cells, negative charge is accumulated at cathode, positive charge is at anode. So, okay, but you know that oxidation will always happen at anode and reduction would always happen at cathode. Okay, this is the basic idea we need to have. We learned that whatever the electrical energy that we are using will be same as that of delta G value. Delta G value can be assessed as minus NF E cell, while delta G naught will be equal to minus NF E naught cell. Okay, we learned something about standard hydrogen electrode where we standardize that the reduction potential of H plus to H2 or H2 to H plus as an oxidation potential both are zero. Hence, any measurement with respect to E cell will be equal to E naught of, let's say, metal reduction plus E naught of hydrogen oxidation. So since this is zero, so whatever the E cell value is, that will become the reduction potential of the metal. That will become the reduction potential of the metal. Given the reduction potential values, we should be able to figure out which is a stronger or weaker oxidizing agent. So suppose if I gave you something like E naught of example, E naught of A plus 2A, and this value is, let's say, 1.5 volts, and E naught of B to B plus 3, value is 1.5 volts. E naught of C plus 4 to C plus 3, its value is minus 0.5 volts. And E naught of D plus 3 to D plus 2, okay, this value is minus 1.2 volts, let's say. Then you need to figure out what are their oxidizing potentials and reducing potentials. And imagine if I connect these two, what is the best cell potential I can make? You can see this is reduction, it is positive value, and this is oxidation, which is positive value. Hence, I can make a cell where E naught cell will become E naught of A plus 2 to A plus E naught of B to B plus 3. Therefore, this is 3 volts. Okay, this is the 3 volts which you will get. What if I want to connect the A cell versus C cell here? So in that case, E naught cell will be equal to, the reduction value is higher here, the reduction value is very low here, which means this can be oxidizing value. So I can write this as E naught of A plus 2 to A plus E naught of C plus 3 to C plus 4. That will be equal to 1.5 minus of, plus of, sorry, plus of 0.5 volts. So which makes it 2 volts. As long as E naught cell is positive, if this is positive, cell is spontaneous at standard conditions. Shell is spontaneous at standard conditions. Standard conditions. So that is one thing we need to understand. Now, if you notice, given these ions, A2 plus is converting into A, B plus 3 is converting into B, C plus 3 is converting into C plus 4, and D plus 3 is converting into D plus 2. So these will become oxidizing agents. So oxidizing agent implies A plus 2, B plus 3, C plus 4, and D plus 3. These are oxidizing agents. If you notice, the value wise, A plus 2 has high value to convert into A, and then we have, okay, 1 minute, and then we have C plus 4, and then we have D plus 3, and then we have 1 minute, B plus 3. This is the oxidizing potential or oxidizing nature. Okay, this is about the oxidizing potential or oxidizing agent trend. If you are to calculate the or compare the reducing agents, then that includes A, B, C plus 3, and D plus 2. These are the reducing agents. Out of this, the highest value includes D plus 2 greater than C plus 3 greater than, okay, uh, greater than, sorry, first one is B is the most or the highest value here, and then last one is A. So this is the power of reducing ability or reducing agents, correct? So this is something which we learned the other class, that how to compare the reduction potential or oxidation potential of various half cells. Okay, so I hope you guys can remember that. Now let's go into detail about how to represent the galvanic cell, and just by the basic notation you should be able to figure out what is the anode reaction and what is the cathode reaction. Okay, so this is a very important area to understand, that how to represent the cell. Check out, there are many type of cells, out of which metal metal ion half cell is one of them, wherein a metal electrode, which is active electrode, is present both at anode and cathode. One second. Anode is also an active cell, cathode is also an active half cell here. So you can see zinc is getting oxidized, copper is getting reduced in this case. Overall, what is happening here is zinc getting oxidized and copper 2 plus is getting reduced to produce this as Zn2 plus and copper solid. Okay. So how do we represent this as a cell? Suppose, just imagine that this copper is at some X molar concentration and zinc is at some Y molar concentration. In that case, how do we represent the cell is this way, that there is zinc solid, which is the electrode. The line always shows the phase change. It is changing into the phase where it is becoming Zn2 plus aqueous ion of concentration X molar. Then a double line. Double line always represent the salt bridge. This is salt bridge. And thereafter, we have copper 2 plus connected. So now we will write this as copper 2 plus aqueous ions, which are of Y molar concentration, which is getting reduced to copper on a copper electrode. So this line basically represent the phase change. And okay, conventionally, anode is usually left, and cathode is usually right. Okay, so that's how you will differentiate this part. Okay, I hope you understood. This representation is what is called as the cell notation, everyone. Okay, this is the cell notation for metal metal, okay, ion electrode, metal metal ion electrode. So please check this out, everybody. It's clear. So I guess the metal ion electrode, how it looks like, everybody is clear with it. See the next electrode. Next electrode is gas and gas ion electrode. Left side also there is a gas based electrode, right side also there is a gas based electrode. Left side, the gas is present, the gas is in contact with a solution of concentration C1 molar. Right side, it is in contact with concentration C2 molar. And what is the reaction that is happening here is H2 is converting into H plus, there is an oxidation. Here Cl2 is converting into Cl minus, that is a reduction. So how do I show this oxidation and reduction, everybody? So please look into it, how we'll show that. Now, this is very interesting because hydrogen electrode will always have a support of an inert electrode, and the inert electrode is a platinum usually. So this is a platinum electrode which you take. So first, how do we write this? We write it as platinum solid. Okay, and that platinum solid is in contact with H2 gas. That means H2 gas is adsorbed on it of a pressure P1, P1 atm, like this you will write. And then that H2 is getting oxidized to H plus ions, which is of C1 molar concentration. Then there is a double salt, and thereafter you can see the next thing in contact is the chloride ions, and thus chloride ions are forming with a concentration of C2 molar coming from Cl2 gas, which is also present on a inert electrode platinum, and this chlorine is maintained at P2 atm pressure. Now this is the cell notation of gas and gas ion electrode. If you have to write the overall reaction of the same, let me tell you how the anode and cathode reaction looks like. Anode reaction is simple. H2 is converting, H2 gas is converting into two H plus ions plus two electrons. While cathode, if you compare, it is Cl2 gas is consuming two electrons and converting into two Cl minus aqueous. So this is the cathode. Overall reaction, overall reaction will be equal to H2 gas plus Cl2 gas is giving 2 H plus ions plus 2 Cl minus ions. What is the concentration here? I mean pressure here. Pressure is P1, H2 gas. Chlorine is P2 and 2H plus is C1 molar concentration, and this is C2 molar concentration. Usually when you write the reaction quotient Q, it is about product concentration Cl minus square by reactant concentration. Now, if there is a gas, you'll always express only its pressure, partial pressure, like this. So therefore, this will be C1 into C2 divided by P1 into P2. This will be whole square, C1 square and C2 square. So this is the Q value. And how do we write the E cell here? E cell will be equal to E naught cell minus 0.0591 by number of electrons transferred are 2 and log of Q value. So Q value, I have written it there. This is how you figure out what is the gas ion electrode. Okay, please do check quickly, everybody. If there is a doubt, you can. Next look into the other cell when you have oxidation reduction half reactions, half cells. In this case, you always have an inert electrodes on both ends, but there are ions within the solution where they are undergoing oxidation and reduction. Like Fe plus 2 is undergoing oxidation to Fe plus 3, and Sn plus 4 is getting reduced to Sn plus 2 at cathode. If this happens, this is the oxidation reduction half cells. What is the anode reaction here? Here we have Fe plus 2 aqueous is converting into Fe plus 3 aqueous plus 1 electron. While reduction is Sn4 plus 2 electrons is converting into Sn2 plus aqueous. Okay. So if you check out the Q value, first the number of electrons should always be balanced. So to do that, what we do, we multiply this equation with 2 and then add to make the overall reaction. Okay. Sorry, this is the cathode reaction. I'll just write down here. Okay. So this is the cathode reaction. Overall reaction includes Fe plus 2 plus Sn4 plus, that is becoming Fe plus 3 plus Sn2 plus. Because you have multiplied with 2, this 2 and 2 will be applied here. So Q will be equal to Fe plus 3 concentration whole square into Sn2 plus concentration upon Fe plus 2 concentration whole square into Sn4 plus concentration. This is about Q. And E cell will become E naught cell minus 0.0591 by 2 electrons log of this Q. Now listen up. When you have this anode and cathode and you're writing this overall reaction here, how do we represent the cell notation? See, We have platinum electrodes here, correct? We have platinum electrodes which is in phase change with, you know, Fe plus 3 aqueous, sorry, Fe plus 2 aqueous, Fe plus 2 aqueous of certain concentration. The concentration given is C1 molar. So we'll write this as C1 molar. Then you'll write it as comma because both of them are in the equal or the same state here. Hence you'll write it as comma and then we'll write Fe plus 3 aqueous changing to C2 molar concentration and then a double bridge. Then we have SN4 plus ion concentration where it is maintained at concentration C3, C4 molar and that comma because again the Sn plus 2 is on the same phase. So then that is C3 molar concentration. So this is about C3 molar concentration and then that line with platinum solid. So this is about the uh, right. So this is about the cell notation. Okay, this is how the cell notation looks like. All right. So please be check with the cell how it looks like. This is how the cell looks like. Platinum electrodes are on both ends. Both these compounds are getting oxidized and reduced in the same solution. Here also it is in the same solution. So please do check. So this type of cells are oxidation and reduction half cells. Okay. Next. Now usually if you notice everybody, one thing you got to realize is which of these half cells, which of these electrode potentials will have more or less reduction potential here. This is based on the data. You can clearly notice that if it comes to oxidizing agent, the highest will be F2 because this has the highest positive value. So first will be F2. The second will be MnO4 minus in acidic condition. In fact, actually, there is slightly better than this. I have not written the value, but that is about O3. O3 is also very strong oxidizing agent. And then comes chlorine, right? And after chlorine, we have peroxide actually, H2O2, which I have not written, but it is peroxide in acidic medium. And then chromate, Cr2O72 minus in H plus, chromate, okay, dichromate. And then we have oxygen, O2 getting oxidized to convert into water. And then we have bromine liquid, correct? And thereafter we have what do you say, bromine and then NO3 minus and then Fe plus 3, Fe plus 3 to Fe plus 2 and that is greater than I2. Okay, this is greater than I2 solid. So this much is the list. I would expect you to remember everyone that which of them is stronger oxidizing agent than the other. Now, when it comes to reducing agent, you can see the highest negative value is for lithium as a reduction, but as an oxidation, it will be the highest value. So, therefore, lithium solid will be the strongest reducing agent, followed by sodium, followed by aluminum. Okay, clear? Followed by H2 gas, correct, in basic medium, followed by zinc, followed by Fe, followed by nickel, followed by H2. Okay, this is how much we need to know. So this is the list of oxidizing and reducing agents based on their respective E naught reduction value. These values are called SRP values, standard reduction potential values. Okay, everybody. So if you find anything highest negative, which means it is a best oxidizing agent. If you find highest positive, that means it is a best oxidizing agent. Okay. So fundamentally, you should know which of them act usually as good oxidizing agent and good reducing agent. Now, if a question is given where cell notation is there and then we need to find out what is the EMF of the cell. E naught values are given. Now listen up to the algorithm how I will solve the question. The first thing I would do is to figure out E naught cell always. So E naught cell will be equal to, you know, reduction potential of the cathode minus reduction potential of the anode. Let me write down that. That is reduction potential of cathode minus reduction potential value of anode. Okay. So you can see reduction potential of cathode, which is getting reduced here, this one. So this value we will have to write 0.337 minus, this is an oxidation potential. The reduction potential will be minus of 0.04. So minus of minus 0.44. This will be the E naught cell value. So which makes it 0.777. This much in volts. This is the E naught cell value. Now if I put the formula, E cell value will be equal to E naught cell minus 0.0591 by, you can notice the number of electrons transferred are 2. So log of Q, which is equal to E naught cell is 0.777 volts minus 0.0591 by N log of Q. Okay. Q value. Now notice this, for that, whenever you want a Q value, for that we require an overall equation. So let me write the anode reaction here now. Anode reaction is Fe solid changing into Fe plus 2 electrons. Then cathode. If it comes to cathode, you can see copper 2 plus aqueous is taking 2 electrons and converting into copper solid. Okay, this is the reduction value. So if I add both of them, then the overall reaction includes Fe solid plus copper 2 plus aqueous is giving Fe2 plus aqueous plus copper solid. So then the Q value will be simply concentration of Fe plus 2 upon concentration of Cu2 plus. So then calculate what is Q. Q in this case given as copper 2 plus Fe2 plus by copper 2 plus concentration, which is 0.10 divided by 0.01. So it is 0.1 divided by 0.01, which makes it 10. Now substitute this back into the equation now. So as you do that, we will get E cell is equal to E naught cell minus 0.0591 by 2 log of 10. So E naught cell we have got this as 0.777 minus this is approximately 0.06 by 2 log of 10 is 1. So which makes it 0.777 minus 0.03, which is equal to 0.747 volts, which is positive, suggesting that this is a spontaneous cell. That this is a spontaneous cell. Okay. So please, everybody, please look into this working. Understand how I gone through the algorithm. What is the first thing I calculated? What is the next thing I put it around? What is anode, cathode? How to calculate Q? Then E cell. Please go through it once quick. It says that the EMF of the cell is given as this much at 298 kelvins. Calculate the value of M1. Okay, clear here? So basically the cell was given. I'll just write down the cell, how it was given. The E naught value of zinc is given, E naught value of cadmium is given, and then the cell notation was given like this, everyone. Zinc Zn2 plus aqueous of 0.1 molar with a salt bridge, cadmium 2 plus aqueous of m molar, which is becoming Cd solid. So we are expected to calculate the value of m. Okay. Well, let me write down this as m1 because that's what is been mentioned in the question. Okay. So again, follow the algorithm, everybody. So what do? We calculate E naught cell first. So you can see cadmium is in a reduced part, zinc is in an oxidized part. So it has to be E naught cadmium 2 plus 2 cadmium minus of E naught Zn 2 plus 2 Zn. So hence minus of 0.4 minus of 0.76. So that makes it plus 0.36 volts. So E naught cell is positive. Then E cell, then we have to check out anode and cathode reactions. Anode reaction is Zn giving Zn 2 plus 2 electrons, while cathode reaction is cadmium 2 plus 2 electrons is becoming cadmium. So overall reaction, if you notice, this would be like Zn plus cadmium 2 plus aqueous, that is giving us Zn 2 plus aqueous plus cadmium solid. So from here I can calculate what is the reaction quotient, which is represented as Q. That implies Zn 2 plus concentration upon cadmium 2 plus concentration. And both of them, I mean, rest of these metals are in solid state. We don't have to consider them. So this is the value of. So you can see as per the question, it is given as 0.1 by cadmium is M1. That's what we need to find out. And what else is given? E cell is given. E cell given here is 0.3305 0.3305 volts. That is equal to E naught cell. E naught cell, we just calculated it as 0.36 volts minus 0.0591 upon 2 electrons being transferred into log of Q1. So 0.1 by M1. Okay. Now this is the calculation that you need to do, everybody. So look at this. So if I take this 0.36 onto the left hand side, so what do I get? I'll get this as 0.0295, and that into 2, there is multiplication 2 as well, that is equal to minus 0.0591 into, sorry, this is log of, so this is basically log of 0.1 by m1. So this into log of 0.1 by m1. Now what you will find out is that this value is exactly same as 0.059. So hence we can actually cancel these two parts, and then you can see log of uh, log of 0.1 by m1 is equal to 10 raised to power of minus 1. So that is equal to, sorry, basically it is minus 1. But now if you remove the log on both sides, it will become 0.1 by m1 is equal to 10 raised to power of minus 1. So m1 is equal to 0.1. Okay. So m1 is equal to 0.1 by uh, why there is a minus value that is coming. Sorry, this is minus. Yeah. That minus will get cancelled. So plus 1 should be there. So that is equal to by 10. So 1 by 100 or 0.01 molar. So this is the M1 concentration that you should get. So please do check, everybody, how we have done the working. So if there is unknown quantity like that, how to calculate that? Please check. See, we need to figure out the EMF, and these values are given. Zinc values here. Okay. And I'll just give you these values of E naught that was missing in the question. Zn to Zn2 plus is basically 0.7 volts, and E naught of silver plus to silver is 0.8 volts. Now we got to use this and calculate the E cell, okay, or EMF of the cell. So basically E naught of the cell will be equal to E naught of the reduction potential at cathode minus E naught of the reduction potential at anode, right? So that includes silver is getting reduced, so 0.8 minus of minus 0.7. Okay, so that makes it 1.5 volts. So zinc and silver, E naught cell comes out to be 1.5 volts. Then you have to figure out E cell. E cell will be equal to 1.5 minus 0. Now notice the overall reaction here. So zinc basically is converting into Zn2 plus 2 electrons, while silver 2 plus is only accepting one electron to get reduced itself. So to equate the number of electrons given and taken, you multiply this with 2 and then add both of them. So then you will get this as zinc plus Ag plus 2 Ag plus is giving Zn2 plus 2 Ag. Okay. So now you can see Zn2 plus by Ag plus concentration here. Okay. That will be Q value. So 1.5 minus 0.0591 by number of electrons transferred is 2 log of Zn2 plus concentration divided by Ag plus whole square concentration. So that implies 1.5 minus approximately 0.06 by 2 into log of Zn2 plus concentration given as 0.01, Ag plus concentration is given as 0.1 whole square. So it is clearly shown that this factor will become 1. So log of 1 means 0. So that makes the value as 1.5 volts only. So both E cell and E naught cell in this case value is coming out to be 1.5 volts. Okay. So please do check everybody. Okay. Clear? Finished? Let's look into the next question. Find the EMF of the cell in the following reaction here. Left hand side there is an anode cell, right hand side it is a cathode cell. Let us first write down overall reaction. So basically here H2 gas plus copper 2 plus aqueous. These two are the source to becoming oxidation and reduction. Both the electrons are two electrons which is transferred from anode to cathode or cathode to anode here. And in that case, what will be Q value? Q will be equal to concentration of H plus whole square divided by pressure of H2 gas. You do not try to change the uh, pressure term into concentration. Reason being, these are ratios, number ratios. So we just need to take the value that is directly given. That into Cu2 plus concentration. This is the Q factor, which is equal to H plus ion concentration is 0.1 whole square upon this is 2 molar into Cu2 plus concentration is 0.01. So this 2 will get cancelled. So Q is half. Q is half. Next writing the next writing the E cell here, that is equal to E naught cell minus 0.0591 by N in this case is 2 log of 0.5. So that E naught cell, if you notice that, clear. Now we need to know these values. I'll just give you that. You see this value will not be given, but you should understand the default. Whether it is oxidation potential or reduction potential, hydrogen is always 0. And next, E naught of copper 2 plus to copper, that will be 0.34 volts. So we can use that 0.34 volts. So what will be E naught cell? That will be reduction minus oxidation. So which is equal to 0.34 volts only. So in this case, we have 0.34 volts minus 0.0591 by 2 log of 15. Sorry, log of 0.5. Okay. So that is equal to 0.34 minus approximately 0.06 and log of 0.5 is 1 by 2. So this is log of 2 raised to power of minus 1. So which is equal to 0.34 plus 0.06 into log 2, which is 0.3. Log 2 is approximately 0.3, everybody. Okay, clear? So using this, when you add all of that, this is coming out to be 0.349 volts, which is approximately 0.35 volts. Okay, so please look into it quickly. Easy one again. It looks like only one part of it. So check out the half cells here. So first one starting with metal ion half cell. So basically this is a metal, and inside solution we have a metal ion like silver dipped in AgNO3. This is called metal half cell. Okay, clear? Now we can write AgNO3 or we can write AgCl also, but just saturated solution. When you have just saturated solution, that means there is no precipitate forming here. So AgCl is the appropriate solution concentration and in which silver is dipped here. So if these half cells are cathodic, so I can say Ag plus 1 electron is giving Ag. This is a reduction potential, and Nernst equation can also be written for reduction potential like this. Okay. Similarly, if you have gas and gas ion half electrode, so you can see this H plus ion is accepting one electron, converting into half H2. This is the cathode half reaction or cathodic half reaction or reduction reaction. In that case, E of H plus 2 H2 is giving H plus 2 H2 not minus 0.0591 log of pressure of H2 power half by concentration of H plus. Okay, this is the E value. Next, metal insoluble salt anion half cell. Okay, what does this mean? See, what if you have a scenario where there is silver metal, but it is been having a paste of AgCl on the surface, and that is been dipped in a solution of KCl. So this is called metal insoluble salt anion half cell. Okay. Now, what are all the reactions that might be going in the solution? Let's see that. Okay. So check this out. The first reaction must be AgCl solid. Okay. That must be in equilibrium with Ag plus aqueous ions plus Cl minus aqueous ions. This is the first thing we'll expect. Second thing, silver Ag plus aqueous must be reduced here because its reduction potential naturally is high. So it will take an electron and convert into Ag solid. So it has now become reduced part. So we got two equations here. This is equation number 1, equation number 2. So you can see, if I write it as the cathode reaction, what I can say, and adding both of them, I will say AgCl plus 1 electron, wherein this Ag and Ag will get cancelled. So that is giving Ag solid plus Cl minus aqueous. Okay, so this is the overall reaction here. Got it? So this is 3. This is the reduction potential. How do we represent the reduction potential here? See, first, if it is on the cathode side, it will always be after double line, which is salt bridge. And after double line, it is the Cl minus ions which are immediate contact with half cell, and that then we write it as AgCl solid, and that is getting reduced to Ag. This is how you represent the half cell for sparingly soluble salts. Half cell, half cell notation for sparingly sparingly soluble salt. This is the half reaction. Got it? What if you have this as the anode? This is the cathode as an electron. Anode as an electron, how does it look like? It's too late. 1 second. So sorry, please check. This is about the cathode half cell. If at all I have to write this as the anode half cell, that means it is the reverse of it, where we have reduction, where we have oxidation. So oxidation of sparingly soluble salt electrode. In that case, basically the reaction equation, look like this. Silver is getting reacted with Cl minus, and it is converting into AgCl solid plus one electron. This is what is happening at the anode. So in that case, how do we write that? Because it is anode, first you will start with the electrode, silver, and what is there in the solution? I mean, before going to the solution, AgCl is present, which is converting into, which is taking Cl minus, and then comes double line. So this type of representation is the anode part of the representation. This is the cathode part of the representation, everybody. Okay, so one is anode part, the other one is cathode part. Clear? Now, while writing the E naught value also, you will write it in the same way. So if you have to write E naught of reduction, then we write it as E naught of Cl minus to AgCl to Ag, and E naught of oxidation. So in that case, you will write it as E naught of silver to AgCl to Cl minus. This is how you can write down E naught of reduction and E naught of oxidation. So I hope all of you understood that how to represent the metal insoluble salt or sparingly soluble salt ion. Okay, please go through it if you have doubt. Right? By this particular diagram, so check this out. What we can do. So what we have here is something like silver, on which we have a silver chloride paste maybe, and then there is a half cell, and on the other side also we have a silver, and here also we have a paste maybe of different concentration. This is present in the presence of Cl minus ions. Alright. This is also present in the presence of Cl minus ions. This is AgCl and this is AgCl precipitates. Okay. And of course, this is the salt bridge. So if at all I have to write the anode part, I will write it always like this. Silver with AgCl solid, and that is converting into Ag plus aqueous. Okay. Sorry, Cl minus. Cl minus aqueous. This is the anode representation. Cathode representation, of course, for anode representation, double line will be at the end. For anode representation, it is Cl minus aqueous, then AgCl solid, and then Ag solid. Okay, so here is the salt bridge. So this will become the cathode part of it. Got it? So this is how you will write down the half cells. Okay, left side and right side half cells for sparingly soluble salts. Now check out how many types of salts we have it for syllabus. AgCl with KCl mixture, Hg and Hg to HgO mixed with alkaline KOH or NaOH, Pb and PbSO4 and H2SO4, mercury H2SO4 and Na2SO4, mercury Hg2Cl2 and KCl. These are all types of sparingly soluble salts here and there. So start with this first one. If you have Hg, HgSO4 and Na2SO4, what might be the reaction state and what might be happening here? See, what is happening here is HgSO4 aqueous that is converting into Hg2 plus and plus SO4 2 minus aqueous. And then we have Na2SO4, got it? That which gives away to Na plus plus SO4 2 minus. Okay, this is how the ionized form of Na2SO4 will be. So if at all I have to write it like a cathode, that means there is a reduction happening for mercury. So what I will write here is HgSO4 solid plus 2 electrons. That will give us, now that will give us, Hg solid plus SO4 2 minus aqueous. This is the cathode part of the reaction where you can see clearly electron are being accepted and this is the product what you are getting. Okay. So how do we write the E naught? First the double line, and because cathode is on conventionally right. So E naught of SO4 2 minus HgSO4 and then mercury. This is about the anode form. Sorry, cathode form. Done. This is about the cathode. So if you know the cathode, we can write the same thing for anode also. I don't think that should be a problem. Next, second one is Hg, HgO and NaOH. So basically in this case also HgO is actually a precipitate and that will be ionized into Hg2 plus O2 minus. Got it? Both of them are aqueous. Okay. So then O2 minus which is released will interact with H2O. It will convert into 2 moles of OH minus aqueous. And if I add both of them, then it appears like HgO solid, right? HgO, sorry, there is water also, right? I need to add water also. So H2O plus 2 electrons, and that is giving out this as Hg solid plus 2 OH minus. Okay. So you can see silver is getting reduced, mercury oxide is getting reduced to mercury this way in basic medium. Okay. So reduction potential will be equal to E naught of reduction potential minus 0.0591 by N log of Q. Log of Q. So we can see E of OH minus to HgO to Hg, that is equal to E naught of OH minus to HgO. Okay, HgO here and Hg, this is the reduction part of it. Okay, so that minus 0.0591 by N, which is 2 log of. Okay, so as per the equation, only it depends upon the base. Rest all are, unity concentration. So this is how you calculate the reduction potential in case if this type of cell is been involved. So I guess this part is clear, everybody. How to understand Hg, HgO and NaOH ka reaction set. Please check. Finished. Right. Let's do about the calomel cell. Okay, let's understand how the calomel cell looks like. What are the equations associated with it? Okay. Calomel cell is a sparingly soluble salt of Hg2Cl2 with mercury. So as a cathode, what you should write is Hg2 plus, that will not ionize. And that is basically taking two electrons and converting into 2 moles of Hg liquid. Okay. And now Hg2Cl2, correct. And that is in equilibrium with, is in equilibrium with 2Hg plus 2Cl minus. 2Hg plus 2Cl minus. So rest will get cancelled. So basically, mm, mm, sorry, not this is 2H plus, my mistake. It should be Hg2 2 plus. Yeah, no, it's okay. Now by adding, you can see this term will get cancelled. So what do we get? We'll get this as Hg2Cl2 solid. And that is in equilibrium with 2Hg liquid plus 2Cl minus aqueous. So this will be the cathodic value. Okay. And accepting two electrons. Sorry, I have to represent that also with two electrons. This is the cathode one. E of reduction will be equal to E naught of reduction, okay, minus 0.0591 by 2, okay. So log of Cl minus concentration power 2. Done, everybody? How to think about calomel electrode? Now see, what about the concentration part? If by chance KCl is zero point 0.1 molar, it is called decinormal calomel cell. If KCl concentration is 1 molar, it is called normal or standard electrode, standard calomel electrode. If solution is saturated with KCl, then it is called saturated calomel cell. And what are the half reactions that could happen here? Please check. So imagine this is dipped in solutions. Okay. This is an inert electrode. Inert electrode. So in that case of inert electrode, whatever the manganate it is there, that will get converted into MnO2. Okay. And the other ions of manganese which will present is Mn2 plus. Mn2 plus. Now you can see there are all of them present in the same solution form. So what is happening at cathode? If there is a reduction happening in this case, what must be happening? That is MnO4 minus aqueous form, correct? And this plus, sorry, there is no MnO2. I'll write down the reduction potential one. MnO4 minus plus 8H plus 5 electrons. So this will convert into Mn plus 2 here and H2O. So in case if I want to calculate the E cell, that is E cell will be equal to E naught of reduction potential of cathode minus E naught of oxidation potential by anode. Sorry. So you can see here. Okay, basically we don't write it as a cell. We'll change that. Let me show you. You can say E of reduction is equal to E of reduction at cathode naught minus 0.0591 by N. Okay, it will be phi log of Mn2 plus concentration upon MnO4 minus concentration into H plus concentration power 8. Okay, this is how you can calculate the reduction electrode potential of this half cell. So that makes it E of MnO4 minus to Mn plus 2 in acidic medium. That is equal to E naught of MnO4 minus to Mn plus 2 in acidic medium, and minus of 0.0591 by 5 log of Mn2 plus by MnO4 minus and H plus raised to power of 8. Please check this out. This is the oxidation reduction half cell. Let me show you. 0 is the E cell, E naught cell minus 0.0591 upon N log of Q. This is what we need. Okay. And if I write the half reactions here, at anode, we have mercury cell, which is 2Hg plus 2Cl minus is becoming Hg2Cl2 solid plus 2 electrons. At cathode, we have 2H plus 2 electrons is giving H2 gas. This is cathode. So the overall reaction is equal to 2 moles of mercury liquid plus 2H plus 2Cl minus Hg2Cl2 solid H2 gas. Okay. So Q is equal to pressure of H2 divided by concentration of H plus square into Cl minus concentration square. So if I substitute that value here, I'll get this as 0.0591 by N. N in this case is 2. So log of Q, which is pressure of H2. Pressure of H2 is given as 1 divided by H plus concentration square into Cl minus concentration is also given as 1, and that is equal to 0.25 because E naught of oxidation for calomel cell is given as 0.25, and you know that reduction of hydrogen is 0. So it is 0.0591 by 2 log of H plus square The 2, if at all I take it to the other end, that will become 0.0591 into log of H plus ion concentration, which is equal to 0.25. Imagine if I multiply minus and minus on both sides. So that makes it 0.0591 minus log of H plus ion concentration is equal to minus of 0.25. It is minus of 0.25. Okay. Hence, we will get this as pH. Sorry, did I forget any minus here? I think some minus should have been there. I forgot. Oh yeah, sorry. Here, when the log is coming up, then only there is already minus existing. We don't have to multiply minus again. Sorry. Okay. So that minus is already existing. So pH into, so this is plus. So this entire thing is pH. So that pH is equal to 0.25 divided by 0.0591, which is approximately 0.24, 25 divided by 0.06. So on solving, approximately you'll get it as 4.16. So that is the pH at which the cell compartment E cell will become 0. Please check it out. If the EMF of the cell is given as 0.48, if the reduction potential of standard saturated solution of calomel is given as 0.244, then I need to calculate the pH of the buffer solution in the following. So here there is a buffer solution. We need to find out what is the pH of that buffer solution. Right hand side there is a calomel cell, which is the anode part. Left hand side there is a hydrogen electrode cell, which is, sorry, this is the cathode part and this is the anode part. Okay. So what might be the reactions that are happening if we write it down? So you will see we have H2 gas is becoming 2H plus 2 electrons. So this will become the anode reaction. Now if you notice the cathode reaction, it is Hg2Cl2 plus 2 electrons, that is giving 2Hg plus 2 Cl minus, and this becomes the cathode. And if I add both of them, then I will get Hg2Cl2 solid plus H2 gas, that is giving us 2H plus 2Hg plus 2 Cl minus. Okay. So this is like the overall reaction what you will get. Got it? Now the Q value for that will be equal to H plus ion concentration square into Cl minus square divided by pressure of H2 gas. That will be divided by pressure of H2 gas. And H plus ion concentration square is what is unknown to us. Cl minus concentration, because it is saturated solution, it is standard. So standard concentration is 1 molar. Pressure is given as 1 bar, so that will also be 1. So it is all about H plus whole square. This is Q value. And now notice E cell will be equal to E naught cell minus 0.0591 upon N. In this case, N is 2 log of Q. So E naught cell value is 0.244. E cell value is 0.48. That minus 0.06 divided by 2 log of H plus whole square. So you can see this is 0.244 and this is 0.48 minus approximately this is 0.06. The 2 will get cancelled and log of H plus ion concentration. Okay. So we just learned that 0.244 plus 0.06 and minus as log of H plus is pH. That is equal to 0.8. So pH is equal to 0.48 minus 0.244 divided by 0.06. This is approximately coming as 4. Okay, so please check. This is how you can figure out the buffer solution's pH. The next part of this topic is about identifying the relation between metal ion and metal insoluble salt of half cells. That is, there is a metal ion half cell, there is a metal insoluble half cell. And what kind of a relation you can get between these two? Because lot of time this E naught value is given and this E naught value is not given. Then you have to know how to relate these two. Okay. Now notice this reactions what I have written. Ag plus 1 electron giving Ag. This is the reduction. This is the reduction equation for Ag plus, and we will write E naught of Ag plus 2 Ag. This is the reduction potential. And if there is an AgCl present in some other electrode, let's say some other electrode there is AgCl present, it is getting reduced. So one electron giving Ag plus Cl minus is the second electron. Okay, and then adding these two here, right? Sorry, the third equation which I can write is AgCl is also in equilibrium with Ag plus and Cl minus. Okay, it is in equilibrium with Ag plus and Cl minus. Close the door. Okay, now how do I relate these two? If for this equation the Gibbs free energies change is delta G1, for this equation delta G naught 2, and for this equation delta G naught 3, then how do we relate these three? So you can see third equation we can get it by taking second equation and subtracting the first equation. Okay, so which means delta G naught 3 will be equal to delta G naught 2 minus delta G naught 1. So let me write down that first here. So delta G naught 2 can be written as delta G naught 1 plus delta G naught 3. And delta G naught in terms of this reduction potential, I can write it as minus NF E naught. Let us write this as E naught 1 and this one as E naught 2. So I can write this as minus NF E naught 2 is equal to minus NF E naught 1 plus delta G3. Delta G3 will be equal to minus RT ln KSP, isn't it? Because it is at equilibrium. If you remember, delta G naught value at equilibrium can be written as minus RT ln K equilibrium. So in this case, the equilibrium is with respect to the KSP. So I'll write it as minus RT ln KSP. Now you can see I can remove these minus signs from all of that, and I will get E naught 2 will be equal to E naught 1 plus RT by NF into ln KSP, which is equal to E naught 1 plus, this RT by F value, we know that is 0.0591 by N log of KSP, Okay. So what is E naught 2 now? This is E naught 2 value, right? Let me rewrite that. So E naught of Cl minus to AgCl to Ag. So that is equal to E naught 1, which is E naught of AgCl to Ag plus 0.0591 by N log of KSP. Okay. So this becomes a very, very important equation while solving. Got it? So you can see we can always use this equation for solving the questions where we need, with this information is given, KSP is given, but this E naught value is not given. In such case, we can always relate two different electrodes. This is a different electrode, this is a different electrode. These two electrodes can be related using this equation. Okay, please go through it thoroughly. Okay. So imagine if the same calomel cell given these three equations here, correct? Then what is the equation that you will get here is E naught Cl minus to Hg2Cl2 reducing to mercury, that is equal to E naught Hg2 plus 2Hg plus 0.0591 by n log of Ksp. So this is what you will be able to derive it using these three equations. Clear, everyone? Please try this once again. This is very useful, right? In a lot of problem solving, this E naught value will help. Now, let us understand what is the thermodynamics that is related in this electrochemistry part here. Okay, so check this out. What is the relation between K equilibrium and E naught cell? Okay, see, we know that delta G naught at constant temperature and pressure will be equal to minus RT ln K equilibrium. Let me put this as equation 1. And delta G naught at constant temperature and pressure will be equal to minus NF E naught cell as well. So let this be equation 2. Now because these two are one and the same, I can equate both of them. So minus NF E naught cell will be equal to minus RT ln K equilibrium. Okay. So from here I can write this as log of K equilibrium is equal to NF by 2.303 RT, right? RT and E naught cell, RT E naught cell. So this I can write it as, N divided by this entire thing. We know that 2.303 RT by F into E naught cell, because we know this value. This is N by 0.0591 into E naught cell. Okay. So therefore, log of Ksp, or sorry, K equilibrium is equal to N, which is the number of electrons transferred, by 0.0591 into E naught cell. Or it can also be written in terms of E naught cell, which is equal to 0.0591 by N log of K equilibrium. Okay. This is the equation that you know how to relate them. Got it? Second thing is what we need to derive is the relation between temperature coefficient and delta SCl. That is delta S, entropy change of the cell. See, temperature coefficient means the amount of E cell that is changing with respect to the temperature at constant pressure. This is called temperature coefficient. And for that, what I can derive is, that delta G is equal to delta H minus T delta S. So if there is any small change in the delta G value with respect to temperature, it should reflect in the entropy change. It should reflect in the d by dt of T into delta S. Okay. What do we assume is that delta H and delta S are constant values over a range of temperature, or a range of temperatures. Well, considering that, because since this is constant, the differential with respect to T will be 0. And here, because there is a T value, it will be only delta S. So hence I will get this as d of delta G by dt, okay, will be equal to, this will become constant. And you know that, uh, sorry, this minus is not there. Yeah, minus of this. So what I can write here, is this value will become 0 minus of d by dt of TDS will become simply delta S, because dt by dt will become 1. So that will be multiplied into delta S. So from here I can write it as delta S is equal to minus d of delta G by delta T, or it can be written as dou of delta G by delta T with minus. This is delta S. Okay, clear. Now you know that delta G can be written as, minus d of NF E naught cell, sorry, E cell, NF E cell upon dt, okay, with minus sign, sorry. That minus and minus will become plus, and that will become NF will come out, and this will become d of E cell upon dt, okay. And this is what we define as temperature coefficient, okay. So therefore, if I take this NF to the left hand side, okay, so what do we get? I will get d E cell by dt, which is the temperature quotient, which I write as eta, will be equal to delta S by NF. Again, this is very important formula for us. How to relate delta E cell by dt. Okay, so from here I can say that uh, if we substitute this back here, that means d delta S can always be written as this delta NF into this. So therefore, delta G, which is equal to delta H minus T delta S. Now it can be written as delta H minus T into NF into dE cell by dt. Okay. So that is equal to delta H minus NFT d of E cell by dt. NFT. So this is another way of representing delta G in terms of temperature coefficient. Okay. Clear? Please go through it quickly. What is the application of this temperature coefficients? Let's see that. Correct. So when it comes to temperature quotient, you got to realize that delta G is equal to delta H minus T delta S. And now I can write this as minus NF E cell is equal to delta H minus T into NF dE cell by dt. Okay, this is what we just did. So from here we can write E cell is equal to minus delta H by NF plus this will become T times of dE cell by dt. dE cell by dt. Correct. So this equation looks like more is equal to y is equal to mx plus c. Correct. Or rather c is this one. This is c and this is mx. So this is like an equation of a straight line, which means if you notice here, correct. So E cell versus, if I plot E cell versus uh, temperature quotient dE cell by dt, correct. If I plot this, you know that this is how it will go if it is about delta H being less than 0. If it is less than 0, this is a positive slope, sorry, positive intercept. If it is less than, if it is greater than 0, that means it is endothermic. In such case, the same equation will go like this, where this time delta H is greater than 0. It is endothermic. Okay. So this is the application of temperature quotient, that how you can relate that with the E cell. Okay. Next one is the efficiency of galvanic cells. You know, just like how we learned in thermodynamics, efficiency eta will be equal to output, right? Output upon input, output upon input into 100. Okay, clear. The output being the delta G at constant temperature and pressure. This is the work done, non-expansive work done. And input as in how much amount of delta H of the cell is present. So that into 100. So which can be written as NF E cell upon delta H into 100. Sorry. Right, everybody, please look into this. So if the efficiency is 100%, that means we are able to convert all of the free energy change in the cell into useful work done. Clear on it?